Hi everyone, I'm Mark Isaacson. The first few minutes of the recording of my tech talk got lost, so I'm going to re-record them now on my computer. So I'll start with an introduction. As I said, I'm Mark Isaacson. I am presenting this tech talk, The Set of Natural Code, through Michigan Hackers, which is an organization at the University of Michigan. About me, I am a TA here at the University of Michigan. I have TA'd 281, which is Data Structures and Algorithms, and 482, which is operating systems. So I've done some teaching, and actually a lot of the talk is motivated from my work in those classes. I'm actually starting work full-time at Facebook next month, so that's exciting. Woo. So let's get into the material. The title of the talk is The Set of Natural Code, and we're gonna have a discussion during this talk. It's about how over time the power of what you're able to write naturally has dramatically increased. It is very easy for you to talk about ideas that only a decade ago would have been really, really difficult and involve lots of sort of magic expert level code that's now at your level. And in some cases that means moving from one language to another, and in some cases a language evolves, like C++ 98 going to C++ 11. We'll see an example of that. So again, they're going to have a theme here of a few different things. It's going to be that things are easy, natural, and expressive, right? That there's going to be a high power to weight ratio of the code that you see versus what it's actually doing. We're going to see a set of repeated themes throughout the talk, that ideas that show up once are going to show up over and over and over again, reinforcing one another, making a sort of really great system that's easy to work with. The case study for this is the D programming language. So a lot of the code we're going to be seeing today is D. We will also have a sort of comparison against C++ so that we can see why things are more expressive and in what ways, where we get efficiency bonuses and all that sort of stuff. All right, so I want to take a moment and encourage you all to ask questions, and I realize that this is a recording now, so I still mean it though. If you have a question, and it's perfectly agreeable that you might, please comment on the video. Let me know. I'll be keeping an eye on this from time to time, or you can comment on my blog. I believe I get an email if you do that. My blog can be found at maintainablecode.logdown.com, and also both in the comments to this video and on my blog you should be able to find a link to the slides for the talk, and they have some extra information, a written down version of what I'm going to be saying. Syntax that you might be familiar with is often highlighted in those comments. So if you've got questions about anything at all, make a comment. I'll try and get back to you. So let's have some context for the discussion, right? Something you may already be familiar with. The differences in, let's say, C and C++. How far did we come when C++ came out? So on the left here, we've got this sort of C-style container. And this is something that I've written. In fact, it's something I've written through one of my university courses here at University of Michigan 381, or something quite similar anyway. The notion is I have a container. Because it's C and C doesn't have a notion of generics, I have to store everything inside it as both a pointer and a void pointer so that it doesn't care about the type. In this case, I'm just using one that is specialized over ints to keep things simple. So there's some interesting stuff going on. The first thing is I've got a function that makes my container. My container, I refer to it as a void pointer so that you can't poke inside its guts and break my invariants. And I have to manually say, make this out of some function. It comes back as a void star. I can then work with it. I've got a normal function. It says add an element. It takes the container as its first argument, right? It's very explicit. And finally, when all said and done, I call container free, give it the container again, and this is how my container knows how to go through and clean up the memory appropriately. So 3 different lines. In C++, they boil down to 1. Vector of int, initialize it with a particular value. right? The initializer list syntax, which if you'll notice those are curly braces there, says put these values into my vector. What's awesome about the right side is that I don't have to do any fancy magic to free the container. I can create it with the memory in there, so it's going to allocate the size it needs straight out of the gate. It's not going to start empty, then later call new or malloc or some other primitive again so that it resizes. It's terse, it's natural, it's expressive, it says exactly what I want it to do. There's no room for error. I can't forget to free the memory because it's just going to fall out of scope, and then the destructor is going to happen. It can't be null, right? There's no chance that the container object is null, whereas on the left, I've got it in a pointer, therefore that pointer may be null. The compiler is going to check the types for me, so it will always be an int that is going in there. In the other side, maybe I'm calling container add elt, but I'm not actually passing in a container, I'm passing in something else. So bad things can happen. We've come a long way. Right? We bought lots of things. We bought safety, we bought expressiveness, we bought efficiency actually, both for the allocation reasons and for having things in the stack. So good wins. I've got another example for us. A square function. So in C we would use a macro. We've got this square thing. The reason we would do it this way as opposed to a function is because we'd want to bleed out all of the bloody efficiency that we possibly could, and what's more, we want to be able to get things moving at compile time so that the optimizer can kick in and make awesome things happen for us. So we're going to do textual replacement via the preprocessor. It should be noted the preprocessor is not really aware of the language. It's cut and paste, copy paste sort of stuff. If I didn't include, by the way, if you'll notice the extra set of parentheses around the x's, it's possible that bad macro expansions might happen and we might see undesirable results. So those are significant and something where if you forgot them, it'd work most of the time but not all of the time, and that's a scary thought. Moving over to the C++. It's templated, right? So there's a little bit more syntactic overhead to writing it down, and then the question becomes, okay, what did we buy ourselves? Okay, the first thing is we bought ourselves some type safety. So we know for a fact that things are going to have a type. The compiler will, there's no expansion problems to have here, right? If I pass in an x, it's a function, it's language aware, so I don't need any extra crazy parentheses because we're not doing replacement, we're actually invoking a function. What's more, because this is a templated function, it will probably be inlined, and accordingly the optimizer will again kick in and we still get an efficiency bonus. It also works with operator overloads, so if I want to do any of that fancy magic, I've got it at my fingertips. In general, there's a trend which is move away from macros, they're evil. So something just to keep an eye on in the future. But this is a couple examples of the evolution that we're talking about, of going from things that are fundamentally unsafe and that are tricky to debug, where you might make an error and not realize it, where it might fail silently, either because in the first example you forgot to free up memory, or in the second example because it works most of the time but not all of the time because you left out a couple parentheses. In the C++, that can't happen. Let's talk about D. So I've got some buzzwords here for you. It's a systems language. It's compiled, right? It's not like Java where it's run on a VM. D is actually compiled down to bytecode. It's statically typed. So everything in the language has a type. If I say x equals 5, I cannot then say x equals hello. So there is a type to everything. You get a choice of value and reference semantics. So at any point in time, you can say whether or not you would like to treat an assignment as a copy, a deep copy, or a shallow copy. And actually, we'll talk about this in much greater detail as the talk goes on, but in D, you don't really pay for anything that you don't ask for in terms of performance. You will have a reference, usually, by default, and a copy via some explicit notion. More on that later. Ints are copied by default, so the rules may seem complicated, but are in practice very simple. There's something called modules. Long story short, it basically just means that you don't pound include things. It's not textual inclusion, copy-pasting of header files. It's actually a well-defined language module bringing together system. If you see import throughout the slides, that's what that's doing. It happens to make compilation more than an order of magnitude faster, to the point where over the summer at Facebook when I was writing in D, I did not actually have my makefile broken up into multiple steps because that made it slower. It was slower to fire up the compiler multiple times than just have it do all the work. There is a garbage collector. It is optional. You do not need to use it, although it does make things convenient, and when used appropriately, it does not slow things down. Noticeably, I should specify. The rest of those things are things that we're going to talk about as we dive in. Except for polymorphism, that's just on there for completeness. It is not actually, I would say, a very big facet of the language, much in the way that polymorphism is not a big part of C++. Let's dive in. So, getting our feet wet. Hello world. I think that there's one interesting line on this slide. Any guesses? No?
Main is board.
No?
We're running out of choices.
We are. Your odds are going up. Yeah, all right.
Is it the top one?
It is the top one. The top one, the one with the shebang notation and all of that, that means that D is scriptable. If I take this .d file and I give it plus execution permissions with chmod, I can just do /b the script file, and it will compile it, it will figure out all the dependencies, do all that makefile stuff for you, compile it, and run it. And what that means is that I can write really powerful programs that compile in amount of time that you wouldn't notice. Perl, by the way, is compiled, if you didn't know. Right? I'm pretty sure this is even faster at compiling than Perl. It's way faster at running. We can do interesting things. What does this program do? Anyone? Feel free to shout it out whenever you think you've got it.
It sorts the lines in file.txt.
Yeah, pretty much. So we're going to read in a file. We're going to look at it by line. Normally that would only give us one at a time, so I'm doing this .array call that says, give me this range, is a word that's going to show up again later, as an array. Just go through the whole thing, pop it into an array for me, sort that, put it back together with new lines, bump it out to output. I think that this has a wonderful power to weight ratio. The amount of text on that screen to make this happen, very, very, very small. Right? That there's not much going on. Yes?
So do all of those just get automatically interpreted as function calls?
Yeah, so we're actually going to talk about that in just a second. This second. So here's the same code. I've rewritten it a little bit. I've rewritten some of it, not all of it. D has this thing, it's called universal calling syntax. Long story short, if you have a line x.sort and there is no sort member function, it will look for a function of the form sort of x, sort parentheses x. So sort parentheses, all that stuff is the same thing as dot. It just takes in whatever's above it there as its first argument. What this means is that we can write this very expressive code really tersely. I actually think that it's a more natural way to read it. I'm going to do that, then that, then that, then that, then that. It's kind of like a list. All right. Let's take a look at the C++. This does the same thing. It does it pretty much as fast, or rather, it copies the data no more or less times. I haven't actually benchmarked these particular examples. I probably should. There's a lot going on here. For one thing, it's really dense. I mean, just compare that trying to read it with this, right? There's a lot of stuff going on. The stuff that's there has to be there in order for it to be as fast as the D, or at least to avoid the same number of copies as the D code, right? I have to move my line. If you don't know what move does, I've got a string. A string is represented more or less as an array. So a pointer to some array and how many characters are in that array. That's a representation of a string. If I say S2 equals S1 and this is S1, I'm going to loop through this whole array, copy that data, pop it into a new array over here, and I've got new data. Right? It's a copy of all the stuff that we've seen. If, on the other hand, I did S3 equals move of S1, what I'm actually doing is saying, this is mine now, it's not yours. That's my array. You're taking it as the difference between a deep copy and a shallow copy. It avoids doing a loop. This happens instantaneously. This one I had to loop through all that data. That's what's going on. So in C++, I've got to move out of that line or else I incur a copy. So mental overhead, something to think about. Right? I don't think most people in 281 you probably don't know about move, but it would dramatically increase your speeds on the autograder. Once again, I'm doing move, a different form of it. I'm moving into this O-string stream because printing stuff all at once happens to be way faster than buffering little bits at a time, so we do that. This does that for you. You don't see a move here because everything is cheap by default. If you want complexity, you ask for it. That's a theme that's going to show up in these slides. Right? If you want more work to be done, if you want more than constant time work, you have to ask for that work. Before we move on, any questions about things we've seen? Because we're leaving basic program lab. Okay, so we're going to be talking about a primitive in D. It is arrays. They're probably best to be thought of more like vectors. They have similar sort of operating semantics to them, but they are pretty cheap in cost. So I can concatenate them if I want with the concatenation operator. They always store their length with them. That's awesome because it makes it very hard to have things like heartbleed happen. For those who don't know, heartbleed's a bug that the world had fun with this summer. Pretty much the problem is C. C strings, if you want to be precise. A C string is a pointer and a length. The length may not be consistent with the data. If that happens, you have a bug. If the length is stored as part of your data, like in a vector, you're safe. So we don't even have the primitive in D, or at least not in the, there's a enforced compiler safe subset that does not include primitives that do not have length associated with them. I can get down to raw pointers if I want to. In practice, you never want to. These are just as fast. So here's the difference. I make a copy, or I use the assignment operator on an array. I have reference semantics. It's kind of like a MOOC. If I call .dupe, which is part of the language, I actually get a copy. It'll do the extra work. So again, the theme of we do things that we ask for and nothing else. And here's where things start to get interesting. I can take a window of my data. I can look at a piece of it instead of the whole thing. I'm taking a picture, which is 2 pointers that corresponds to everything from the 1th position element to the end. I could have also written r.length there, would have meant the same thing. The cost in memory is a window. It's a couple of pointers that look at the same data. There's no copy. Let's write a first algorithm in D. What does it do? It's find. Find in my array the element 2. We're just going to decide the way we have the return value set up is you get a slice back. The slice contains everything, including that element, to the end of your original range, or in this case, array. Right? So we're just going to look at everything from where it is to the end. If we didn't find it, that happens to end up working out to the empty slice, nothing inside. The reasons for that will become clear when we generalize. And again, you can see I can do array.find, patterns repeating themselves. I think it's very natural to do that. Yes?
Unit test, I'm guessing, is another primitive that just built it that is like the flag.
Yeah, so it's kind of a philosophy of the language. You will write unit tests. Why? Because it's a blue word, it's a keyword.
it is very, very frowned upon in the D community to write code and not immediately write tests. Why do you want to do that? Well, yeah, you show that your thing works, but it's kind of more subtle than that. If I test my small components, if I write a unit test that says find works, actually I want to be on this slide, then I know that the code that uses find, if that's broken, find is not broken, most likely. I have to write a good test. It gives you confidence in your program. It makes you able to dev much faster. I re-implemented Project 482 recently. When I took the course, I got an 80 because when you put things together, it's really hard to make sure that they come together well. You don't know where the actual problems are. So test them. I tested this time, didn't have that problem. Okay, so let's go through the actual code. This is templated, right? If you were confused for a moment, there's parentheses T and then some stuff. In D, we use a second set of parentheses as opposed to less than and greater than to actually represent our template parameters. It turns out that it's easier for both the compiler and the human. You've been matching parentheses since you learned English. So we do it that way. Overview of this code is, while there is still stuff left in my haystack, the thing I'm searching, and the thing that I'm looking at isn't what I want, look at a smaller portion of it. So it'd be like saying, is H the character I'm looking for? No? Okay, let's look at this part. Is E the thing I'm looking at? No, let's look at this part until you get the end. What are things that we like and things that we don't like? In general, anything on the slide that you like or dislike? Yeah?
It seems kind of weird that you're using haystack to refer to the array, but also sort of the thing that you found in it.
Ah, yes, okay, I can see that. So just kind of a nomenclature thing. Yeah. Other thoughts? Yeah.
It's kind of weird that find is returning like a subarray.
Sure. So I would argue that when I call find, let's say in C++, I'm going to do one of three things. I either want to know, is it in there? And I guess maybe four things. Is it in there? Is an easy answer, yes or no. It is in there, and I want some other data on it because it's a struct and it holds more than the thing I searched for it to find it. I want to know everything up to that point, and I want to know everything after that point. This gives you the answer to three of those questions right away, and with a standard library function, you get the everything before it as well. So, or just some manual slicing stuff. So yeah, it's kind of weird. I think that the reason why it's done this way will make more sense later on, but it also helps you get three of the four answers to the questions you probably want to answer very quickly. Other thoughts?
And the last couple of lines there, you omit the first argument to find. You use the array dot find.
Yeah, cool. I like that. So, personally, my favorite thing on the slide is, well, yeah.
Yeah, can I ask a question? Does D handles garbage collection automatically?
It does, yes. My favorite thing on the slide is the unit test keyword. Not even kidding. That's actually my favorite part. Unit tests are wonderful. But there's something on here that's less awesome, right? If I was comparing this to the equivalent C++ version of the find algorithm, it would look different in that it would have two iterators in there instead of one range, or instead of one array. Are they of equivalent power at this point in time? The answer, I won't make you wait, is no. In particular, this only works with arrays right now. Right? If I pass this a red-black tree, it's not going to know what to do with it. I can't slice on a red-black tree like that. I can think of more esoteric things that I can throw at a find function. And the code as it's written right now does not have the operators to search over those, but it should. So the question becomes, what are we doing? Or more importantly, what is the semantics of what we're doing? There's a difference that I talked about in my talk last year. Asking, what does something do, and what does something mean? what this does is say, is haystack.length greater than 0? But what does that mean? What does what's in the box actually say? What are we asking?
Is it empty?
Is it empty? Awesome. I like it. So what about haystack of 0?
Wrong numbers.
Yeah, so I heard the first thing or the next thing. And what about the last line? Just slice off the container.
Tail.
Yeah, tail, basically. Give me what's left. So we'll rewrite it that way. I changed the template stuff in the signature, so now we take in a generic thing. We've got empty front and top front. This is the input range interface of D, right? This is the meaning of what we just did, and it's semantically all that you need to describe iterating through something, right? It's just the very basics of what do I need to actually go through some amount of data. Yeah?
Is there a reason that top front has parentheses but empty and front do not?
Mostly because I would think of them kind of more like data members than functions. At least, so in D, at least the newer version of D, the parentheses, if you have no arguments, are totally optional at all times. So if I wanted to, I could add parentheses to any of them or remove them from the pop front. I think of empty and front as more like variables, more like properties, because they actually return something, whereas pop front is more of a function. So it's stylistic entirely. Okay, so we've got this interface, great. The question that comes to mind is, well, does that work on arrays? Arrays are built into the language. Arrays don't really have functions on them. It's got a .length property and a .dupe property and like a .size of thing on there. That's built into the language, but very little else is built into the language. So I've changed my function signature. Maybe now this will work with red-black trees, but will it still work with arrays? Do I need to have the overload that I just had before? And the answer to that is no. I can implement these functions on arrays. Right? I've defined an empty function. We'll talk more about the syntax in just a moment. Why is doing this, is properly implementing this interface sufficient to have this code work on arrays?
Because you were talking about this before, it finds, just if it can't find the member function, it will go look to see if there's any member functions that match.
Exactly. So we have that auto rewrite of x.sort becomes sort of x. And that happens even if I'm talking about ints, primitives, arrays. So what we've done is the boundary between what is a user-defined type and what is a built-in type is very, very small, and actually the community is working to make it 0. So I can extend arrays, which is awesome. I can give them extra stuff. Things that might be interesting to you, const there has parentheses. That's so that I never have the case where I'm wondering if I see const star const on a pointer, which const talks about which constants. That's a really annoying thing. There are websites which are designed to help you read constness in C++. You don't need that in D, there's parentheses. In-out is kind of interesting. It says, take the constness of this thing and make it the constness of that thing. So if it came in const, it goes out const. Otherwise, it's fine. And there's actually another thing called immutable, and you would carry that over as well.
So when you find that method,
Yes.
You have those template types R and T.
Correct.
But nothing really enforcing that those methods actually exist. So obviously, like,
Oh, yes.
once you have something in, you could check, if it doesn't exist, then have some sort of failure. But
Sure.
I guess this would happen when you're trying to execute the method rather than when you're calling it.
So there's a buzzword coined in the C++ community called S-fini. Substitution failure is not an error. And basically what that says is, for some types T, if we try and call find, we will try and resolve this function and compile this function. And if we don't have an available empty front or pop front, you will get a compiler error. Or rather, I believe what would happen is it would look for another overload and then eventually perhaps get a compiler error. but it's very much like C++ in that you can throw anything at it, but if it doesn't meet the requirements, you'll just have a compilation error. We'll actually see a way a little later on about how the compilation errors can be made much cleaner than, let's say, 50 pages worth of template jargon in D. And the actual standard library version of this would include one of those, but for brevity, I did not include it on the slides.
So you solved the problem with having it too specific with
Yes.
the arrays, but you've changed functionality. So if you give it, for example, red black tree, you just start popping things off of it. That's what you want to do in this case. Because you're calling pop front on something that is not necessarily what you want to be. I'm calling on a haystack.
I'm calling top front. So I have an example with red black trees in a few slides. We will be calling top front on a range over the red black tree, not on the red black tree itself. If that makes sense. If it doesn't, ask me again when we have that example. Okay, so the question, how do I implement these? What goes in the first body? How do I check if an array is empty? Array.length, but yeah, right? It's the same code we had, we just moved it out into some function. So again, I'm going to get the first thing out of the array. I'm going to look at a smaller window of my array. These functions should take very little time to implement. And here's that example, right? So now find works with arrays again, great, nothing new. I pull in a red black tree from the standard library. I get an range off of it by just doing an empty subscript operator. That range implements front, pop front, and empty, so I can search. So when I'm calling pop front on there, it's on the range that I generate from here, not on the tree itself. It's a view of the tree.
So if you're already calling with the view of the tree, why does it matter if you define it for ranges, as opposed to with the pop back, the pop front you had?
You're asking why this instead of this? Because this operator would not work on a red-black tree. I cannot slice a red-black tree.
You can slice the range you create off the red black, you're not?
Actually, can I? I'm not actually sure that. No, I don't believe that I can. I cannot look at I cannot use the slice operator on a red-black tree range. I believe it is a bidirectional range, which is more limited. Think about it like the difference between a random access iterator and a bidirectional iterator from C++. If those words don't mean anything to you, by the way, they don't have to. Yes.
You use this word range a lot. What exactly is a range as opposed to?
Sure. So a range in this case, we've defined a or an input range as anything at all in the world that implements those three functions. Anything. Or that has the non-member version of the functions that would allow it to be called like its member functions. Anything that looks like an input range is an input range. Similarly, in C++, anything that looks like an input iterator is an input iterator. Yeah?
So those on the slide, we had to write those ourselves. These aren't in there?
They are actually in the std.array library, which is included as part of the standard library. It's just a great example. Right? We're implementing it ourselves to show that it's really easy to do that. As is fine, by the way. An even better, more beefy version of fine. All right, so we've gone through that. How about another example that's a little bit more interesting, right? Something that you probably haven't done before. What if I wanted to search over some infinite sequence? Search over the powers of 2, or an arithmetic sequence, or a geometric one. That would make sense. I can say, is 512 a power of 2? How about 15? Is that? So we can implement a range interface to make that happen. There is something interesting on these slides. Something that probably strikes you as unusual. Any ideas what that is? What I might be talking about? Yeah?
Exclamation point 2.
Yeah! That thing. So what that says, that is how indeed we pass template arguments, right? Because we're not using the less than, the greater than symbols. What we've actually got is a bang character, and then if there's only one argument, you have that one. If there's more than one, you need a second set of parentheses. So it could be bang parentheses 2 parentheses, that would be fine too. I like to think of them as compile time arguments, runtime arguments. Runtime ones are mandatory, compile time ones are not. Actually, runtime ones runtime ones are mandatory in most cases. Yes?
Is there a reason why one of the asserts does not have a bang in front of the power?
Because 15 is not a power of 2.
Okay.
Yeah, two different meanings for bang. This means not. This is being used when I'm calling the function. It means pass an argument.
Okay.
Okay, so here it is. I would ignore empty. I've written that just so that we won't overflow and actually loop forever, but there are infinite ranges in D. This should strike you as a just kind of very simple recursive definition. It's get me the value. When I want to look at the next one, I do a multiplication, the value of some private member. I could phrase it as a question, but I'm just going to go ahead. This was missing. What would be problematic if I didn't have that there? And we'll talk about what exactly that is in a moment. But what would be the problem if I used this version instead? Nope. Actually, yes. Huh. That might have actually caused a compiler error. All right, maybe I don't need that. But I was more thinking the multiply by base, you get an infinite loop. So either way, we don't like that. This is what I was talking about before. It's a template constraint. So this is templated on base, so it appears up there in parentheses. And in particular, you'll get a compiler error in this case. If it's equal to 0, it'll be a nice message. It says, hey, you broke the constraint, as opposed to 50 lines of template. All right, why do we care? I've shown you what some idiomatic D looks like. That's all well and good. You know, this talk is not really meant to be just, oh look, D. That's not what this is about. It's about things being more natural. It's about things having more power, being more expressive, using less memory, having better runtime. So why do we care? Well, reason one, although it's actually probably the least important, is that it's just convenient, right? Instead of a couple of iterators off my vector, I'm just going to pass in the array. In this case, the array is a range, so it works just fine. I'm assuming you pound include, or not pound include, never pound include in D. Doesn't exist, for one thing. You import standard array. So you have the range interface. You can do that. There's a subtle thing going on here. What can happen in this one that can't happen now? I'll give you a hint, it's a security problem. Yeah?
End might not actually point to the end of the vector.
Yeah, so in this case it does, but I'm passing in a container and how big it is. What does that sound like?
Heartbleed.
It sounds like heartbleed. It sounds like C strings. We know this is bad. We built standard strings that you don't have those bugs. And yet we still have that class of bugs in C++. You don't have, it is much more difficult, much less idiomatic, to write D code that will heartbleed. Okay, 4 lines of copy. They all have the same problem. What's the problem? No, yeah, I don't. Say again?
You never pass in the size of power.
So that is in many ways the cause of the problem. What is the size of apple?
0. You create the size of the I didn't say that you just run over it with the right size of the official.
Okay, yeah, so I'd loop over and try and write like 5 things into it, or in this case, quite a few things. Why is that a problem?
It hasn't been initialized to a certain size yet, so...
Yeah, it's empty. There's nothing in there. Right? This is a bug I see all the time in office hours. Out has no data. If I try and write into it, I'm going to get a segfault. Or maybe not. That would potentially be worse. But there's no space allocated. So I cannot copy data into it. That happens in all 4 lines of code. You might be asking, okay, well, if I'm trying to highlight the differences, why in blazes did I show code in D that also has this problem? The difference is, over here, you non-deterministically get a segfault. It may or may not crash, and it will explode, not just die quietly. Over here, things know how big they are. In particular, there's something called a precondition in D. You can write it. I've got a function foo. I can do brackets, or no, rather, yes. No, in, which is a keyword, brackets, some precondition stuff, then the body of my function, some other stuff. It's not too common to see that, but you will see it. And one case you'll see it is in algorithms like this. The precondition set checks for you. Is out big enough to copy that stuff? Because we know how big that is, because it knows its length, or at least it knows when it's empty. And we know how big that is. And if you can't do it, you get an exception, a clean error, instead of a horrifying error, or an assertion maybe, but something that will always stop it before you've written data, before you've caused problems, something that will describe what is happening to you. You don't need to open GDB or Valgrind. You know what's going on. And perhaps the best part, this does incur a runtime cost, but if I compile with a particular flag -release, preconditions go away. Right, so there's no cost in practice. Okay, so we get some safety. It's convenient. There's other stuff. We can write modifiers. If I want to look at this, if I want to sort this in reverse order, so 5, 4, 3, 2, 1 instead of the other way around, I can either use reverse iterators or I can call .retro. It's actually a non-member function. Here's an we'll come to an interesting difference in a little bit. I think that line is easier to write, but you can do that in both languages. How about something more complicated? I would like to get the even numbers, so 2 and 4. Over here I've got a filter function. Filter is kind of interesting. I pass it this anonymous lambda function. We're going to go through all the elements and call this function on each of them. For each A, if it's divisible by 2, great. Over here we've got some C++. It will also get me out the even numbers. I say copy if, going through that, we have a lambda function, do the even numbers, and a back inserter now, so we actually allocate the space that we need. The difference between this code and this code is, first of all, this is really bloated, right? Even if I just, there's a lot of stuff going on, poor power to weight ratio, and also this makes a copy. This makes a copy of the data. This does not. The filter code does not. Filter basically says, cool, either when you call front or pop front, one or the other, not both, I'm going to say, is this even? If it's even, I'll show it to you. Otherwise, I'll skip it. I'll go to the next thing that is even, and maybe exhaust my entire array. But it's a view. It's a way of looking at the data. It is not a copy of it. It's a common thing you'll see in D. You get different perspectives of data rather than copies of data. That's awesome. For one thing, it's constant memory. No extra runtime hit. I can make a copy if I want to, by the way. This is a little esoteric, but I actually had an example quite similar to it when I rewrote my 482 product. I was given a fully qualified file name. So all the way from root, the directory, the file, I wanted all of the different pieces split up and in reverse order. The interesting thing going on here is I'm taking hello, reversing that word, getting the world word out, and putting them back together. And in all of that, I've made no copies, right? I've modified not just the original range, but pieces of it, right? I can reverse a portion of the original range. If I took instead of .arbegin off of the original string over here in the C++, and I just passed some iterators into a function that said, break off the first word for me, you actually can't do that. You need the original container to get a reverse iterator. At least I think you do. And that's not so fun. So I can work with pieces, I can put them back together. This, by the way, uses constant memory. It's also a view. Here I do some copying, and quite frankly, the code is ugly as hell. There might be off by 1 errors in there. It's not anywhere near as nice. So why ranges? They're safer. It's very hard to write the code that is wrong. They're more memory efficient. We actually didn't talk about that, but long story short, if I've got 2 iterators to a red-black tree, they both need to point to that tree. If I've got one range that knows how big the tree is, I have one pointer. They're convenient, less code, great power to weight ratio, and I can write these modifiers, and that's really cool. That's what's awesome, is that I get my data, I can look at my data in different ways, constant memory, same amount of runtime, pieces of it, whole parts of it, anything that I want. If I take a slice of an array and I pass it to a function, it is still an array. Behaves like an array. I cannot treat a pair of iterators off of a vector like they're a vector. Why is this not in C++? I'll give you a hint. It isn't that we can't write it in C++.
Backwards compatibility issues?
No. I mean, if I wrote ranges in C++, I'd write a new sort function that took a range instead of iterators. Why don't we have this? Why is this not in each of your toolboxes? Why are we not using ranges in 281? Well, that's why. Raise of hand, how many people think that they can properly implement a C++ iterator? Any C++ iterator?
You have to in 381.
Correctly.
I did.
I want to see the code later. It is non-trivial. Even if you remember all of these function signatures, and by the way, you need all of them according to the standard, you can, in practice, get away with writing less of them, but the standard says you have to have them. Things are very subtle. The difference between the assignment operator on an input iterator versus a forward iterator, I did not know what that was until a couple of days ago when I was doing some research for this talk. They have a forward iterator and an input iterator implement exactly these functions. No difference in the functions that they implement other than how they implement that assignment operation. It turned out that this is really, really difficult. And by the way, in C++, you also have to have a version of your iterator that works when the container is const. It's a hard problem to solve. It's actually one that D hasn't fully solved either, so I won't give it too much crap for that. There's a whole subset of Boost, which is dedicated to trying to make iterators easy to write, and they're still hard to write. So that's why you don't see very much of it. D is very simple. We did it twice on slides with big fun, right? It's easy, so you get free lunch. There actually is a Boost range library. There is a proposal for ranges in C++ 17 that may or may not go through. It's interesting because it's building on top of iterators as opposed to using it as the bottom primitive. It'll probably be less powerful. But it is coming. So a concept that should hopefully be coming to you quite soon. More POW stuff. Once again, I'm rewriting the function using the 2 dot notation instead of POW of 2, 3. I think, again, there's one interesting line on this slide. Any guesses? Yeah, it's a static assert. Why?
This is different than the other asserts.
Okay, how is it different?
I'm guessing that's a compile time assert.
Awesome. Yeah, so this happens at compile time. I said, take my POW function and invoke it at compile time. Instead of doing work at runtime, do it at compile time. We can do that. This, by the way, is D. Why might we want this? Well, hash tables, a great way to have their sizes is as powers of 2 plus or minus 1, I forget, it's been a while. But that's a reason why you might want this information in compile time. And I could hard code this number, but it's going to be confusing, and somebody who goes in to look at it later may say, what the hell is this number, and change it. So have it make sense, have it be self-documenting. More motivation to come. Here's some C++. This does that. By the way, here's the C++ version of the static assert. This is something called template metaprogramming. It is actually something that shows up in interviews with finance companies, certain finance companies. Professor Markov actually gave me either this or Fibonacci example as something he knows happens in finance interviews. Yeah?
If you're interested in more...
I was about to say that. Stealing my thunder. So, if this code is intriguing to you, if you want to know more about this mess, my best friend Andy's giving a talk on that mess on December 3rd. It's going to be fun. I'm going to be there heckling him. You haven't been heckling very effectively, Andy.
I haven't
Step
needed
up
to.
your game. So,
Question.
yeah,
Can we avoid using templates by using a constexpr function?
we're going to get there. There's a reason that says C++ 98. So, ye old C++ times, right? This is how you do this. Actually, in C, you could actually do it with a macro as well, which is interesting and may or may not give you the same compile time effectiveness. It probably does. But we'll come back to why we don't want to do that on the very last one of these slides. 3 slides there. So what does this do? This should look very complicated to you. So we've got a struct, it's templated, it takes in a compile time, 2 compile time numbers, a base and an exponent. Yes, you could have templates that take instead of types, values. So this is what it looks like when you take a value. This is what's called a partial template specialization. I say, I only care about that one now, we're going to let the other value be 0. So in all cases where this is 0, where the exponent is 0, the value is 1. It happens to be a 1 that is an unsigned long. Otherwise, do some recursion, scope into the exponent minus 1 case, do the multiplication, get that out. If this doesn't make much sense to you, go to his talk. We got something better in C++ 11. I tack on this funky constexpr keyword. It stands for constant expression, as in I can use it as a value in a template. And it says you can now invoke this function at compile time, or runtime for that matter. I write it kind of like a normal function. I say, okay, am I in the base case, yes or no, do the thing. Static assert, get the same value out. I call it much more naturally this way. Great. Another example of we added some more primitives, your power as a programmer just went up. You don't need to know how to write this anymore. You just do that. It's easy. Easy. Cool. So we can do that recursively. One fun fact, this piece of code has to be written almost exactly this way or else it won't compile. The language basically says your functions that are constexpr may have exactly 1 line in them. If I wanted to, instead of using the ternary operator, use an if statement, it would not compile. There's some restrictions in C++. Okay, they saw the folly of their ways. C++ 14, you can have if statements, you can have loops now, as long as they only modify data that is created in the scope of the function. You know, as long as you don't touch anyone else's privates, you're golden. So,
But this is a talk on the D.
moving on. All right, so C++ 14 gives us permission to write functions more like how we want them to. I can't modify anyone else's data, but I can modify my own data. So we can write things differently. There's a reason why this code is better than this code. Any guesses? Yeah, what's the difference? Recursion happens at compile time. The compiler will memoize it for you. It's great. This is the part where you're supposed to be like, but wait, there's a special case. They're actually, well, nah, you'll never get it. constexpr says I can call it at compile time. So what's the problem? Can is the operative word.
We don't always.
Yeah. And what's the problem if I call it at runtime?
Recursion.
Yeah, it's the recursion. So at compile time, who cares, right? It uses a few extra stacks, but it turns out that they get memoized, which is a way of saying optimized in a particular way. At runtime, the difference between this code and this code is this code uses O of n memory. I call this function as many times as I've got exponent, right? I put that many stacks onto the stack string. That's a lot of memory. Over here, I just multiply a number a bunch of times, right? Constant memory. No increase of memory just because I changed the exponent. So why do we care that I can write code this way? Well, because it makes it more efficient when I want my runtime function. Otherwise, I'd want to have like a version of POW like this for compile time and a version of POW like this for runtime in C++ 11, let's say. So you'd have two different versions. Who likes that? That means more things can go wrong. In D, we have something called compile time function evaluation. I write a function. I call it at compile time. It's that simple. It is this. It is the same function. It is no different. There's no constexpr keyword. Any function that you write, almost any function that you write, will work in D at compile time or runtime. So the find function we wrote, compile time. The POW generator thing, compile time. The sort function, compile time. It's great. You'll note actually that I use the POW generator here, just to show that like I can do some complicated things. I say, POW generator of my particular base. Pop off that many things, get me the front. That's another perfectly fine implementation of this function in D. A delicious aside. I like to cook. There's a couple cooking things on here. There's something cool going on. So you'll note that I have in the unit test, I make my silly struct, I add them, and I multiply them. But there's only one function up there. Any guesses what's going on? Yeah.
You're generating the functions for those operators at compile?
Yeah, I'm doing some code generation. So op binary is templated on a string. That string is the symbol plus, the symbol multiply, the symbol bit shift, whatever it happens to be in this particular invocation of the operator. And all I'm going to do is I'm going to say, you know, when I implement my operators, all I really want you to do is do exactly the same thing as if it was on my int. So do that. Here's a string. Return a new silly struct with my value, the operator, whatever it happens to be, and then the right-hand side. I concatenate the operator into that string, and Mixin says, take any string that you've got at compile time and compile it. Right now. Right here. Compile some stuff. And I can generate strings at compile time because I've got compile time functions, including the concatenation operator, and then do stuff with them. So I just bought myself something like a dozen different operators in 3 lines.
So op binary is a special method like operator or whatever in C++.
Yep. Yeah. It's not a keyword because it only actually does something in this context. But yes, it's kind of like the operator keyword in C++. It has special meaning. Yes.
So how can D claim to be a systems language and support stuff like that?
Because Mixin only works at compile time. It is not eval, right? Eval is like, I forget whether it's JS, right? It's like JavaScript or PHP, and you pass in some string, and it happens at runtime, which is bad because some attacker comes to you and says, here's some data, and comma, squiggly special characters, and here's some more code for you to run. I'd like you to run this. You eval that, and all of a sudden you have a security problem. Here, they're probably not attacking you while you're compiling. So anything that you do is your own fault, and it's just a code generation thing that happens in compile time. Awesome. So, all right, this is a little esoteric. It's cool because I can implement a bunch of operators really quickly, but why do we care? This is an awesome slide, and it's not going to be immediately apparent why. I have two different regex engines. I make them with regex and CT regex function. They search through patterns that are pretty much the same. The pattern is not the important difference. What is interesting that is different between the two?
One looks like it's generated at compile time.
Yeah, so we've got that bang character in there. I'm passing in the pattern at compile time. Most of the time you know your pattern at compile time. You're not going to change the pattern because somebody inputted something. You're going to run the pattern over the input. So we tell the pattern to the regex engine at compile time. All right. Does that bias anything more than a, copy of the pattern at runtime? Turns out the answer is yes. Turns out the answer is hell yes. More is better. This is the one that's at compile time. This is the D1 at runtime. D has the fastest regex engine in the world. It is faster than V8. It is faster than RE2. It is faster than any regex engine you probably use. It is not because D has the specialist in regex, the best ones in the world. That's not it, right? If you compare D's runtime regex against the rest of the world, we're pretty meh, right? There's no real magic sauce in the runtime one. But you gave me a pattern at compile time, and I've got all the time in the world at compile time, right? I can do extra work then. And in particular, I can leverage the compiler's optimizer. Compilers are great at optimizing. We've spent hundreds and hundreds and hundreds of man-hours optimizing compilers to do awesome things like dead code elimination. If I know the pattern that you've got, I can put together a finite state machine that works only for your pattern, exactly for your pattern, instead of some general purpose thing that works with Joe Blow, right? So it's fast. It's awesome. So here's some tools that were used by some clever people to do an awesome thing. All right, so another slide, we're also using mixins here. This is kind of a repeat-ish, or a repeated theme from my last talk. I've got phone entries, named the phone number. And Bob and Jill, I throw them in a red-black tree. Why a red-black tree? Well, because I want to print out a phone book in alphabetical order, so the order matters. I print them out, cool stuff. Two questions. Where's the mixin? And why do I love this code?
Assuming the mixin is in the red-black tree. And you're finding the operator last time.
Yeah, so this is a string. It's going to translate that into some code later on. I'll show you exactly what code that is. Why do I love this piece of code? Yeah.
So it's really easy to specify the comparator, whereas like in C++, you have to define a custom struct with some operator parentheses to call it.
So that is actually very nice, but that's not why I love this code. It is an awesome thing that we can do that in one line like that, but it's not the real reason why I think this is awesome. What would the equivalent C++ look like? Yeah, there's templates here too. Well, I'll give you a hint. It's this part. I'm saying entry.name and entry.phone. It's very clear what I'm talking about. You know what it means. So how does it compare? Pair being the operative, horrible, kill it with fire word, right? You've probably seen code that looks like this. It's entry.first, entry.second. Great, what are those? And in particular, I've been actually shadowing that guy at 281 office hours, and I've seen bugs that are caused by people forgetting to write them, because why would you ever write first or second? It's not something you think about when you're talking about a phone entry. It's just like not in your head, so you wouldn't write it, you'd have a bug. An easy bug, but later on when I want to read this, I have no idea what it does. So I think that that's something pretty special. In particular, I think that this is pretty gruesome in C++. It's the only language for which it's this bad. Going back to how the mixin's used, it translates the first line to the second line. That's an actual lambda function. You don't need to know the syntax for that really, but that's where the mixin was. Well, we're at the takeaway slide. Sweet. So I've shown you some cool things. I hope you think they're cool anyway. We've done some stuff. I'm being very vague right now. Let's be less vague. I've shown you comparisons of code. We've written code that is really, really expressive, really small number of lines. If you think back to that very first example where I show you we sort a file and pump it right back out. There's not very much code that you need to do that. And that code does it alarmingly fast and memory efficient, right? It is as easy to write code as if you're writing Python, but way faster. Perhaps even easier than writing Python in some cases, right? I've shown you templates that hopefully feel way more natural to work with than C++, because there's just less garbage on the screen, right? It boils it down to what you actually need. In general, the theme is things that are natural to work with. Some of them are natural to write. So, for example, it's very natural for me to write a templated function that does fine. That shouldn't strike you as something that is very difficult to do indeed. And some things are very difficult to write, but very easy to use and leverage because somebody else was clever to put it in a library, like the compile time regex. We benefit from all of that stuff. We have better primitives indeed. We have ranges. Ranges are safer, they're more memory efficient, they're faster, they let me be more memory efficient. We took our primitives, we made better ones, we do things easier, more conveniently, easier to read, easier to maintain, faster, whatever. That is what's going on today. That's what we've been talking about. All right? It's more natural and still fast. We've talked about the meat. Here's just something if you're curious. A lot of what we talked about is coming your way whether you want it or not. Right? It's coming to C++. We have constexpr in C++. They've relaxed the rules. I wouldn't be surprised if they do it again. It's not as good, but it's there. Universal calling syntax, that x dot sort stuff, there's a paper for it. We may get that in C++ 17. Ranges, there's a paper. Unit tests, there's a Google horrible macro framework that you'll see in industry if you use C++ in industry. Also, promo, I actually published my own thing that lets you write unit tests exactly like D does. It's on my GitHub. Feel free to steal it. You have my permission to use it, although if you want to use a class, you will need to ask your actual instructors. I suggest asking them. It's awesome. It's very hard to understand, though. And then there's some other stuff that we didn't talk about that is in D and might be coming to C++ in some form or is already there. So things are coming. Credit where credit's due. The first three things on there are things by Andrei Alexandrescu, my mentor from this summer and friend. The last thing is the guy who gave the talk about the compile time regex stuff. If you want more on that, it's there. Any questions? Bombarded you with a lot of information. This is the end of the talk. Yeah?
Where is D being used?
Where is D being used? Great. It is being used at Facebook, among other places. So we use it for a few different things. For over a year now, it has been our preprocessor for C++ and also our linting system for C++. We actually rewrote the linter from C++ to D. It had less lines of code in the D. It was faster, actually quite a bit faster, and generally more readable. And that's, by the way, a direct translation, no mix-ins or anything complicated like that. Just translate it, don't be fancy. So overall win there. And faster compilation by no small margin. My project from the summer was also an ODBC driver in D at Facebook. There's a game company that writes things in D. There is a big data company that exclusively writes in D. I think they're based in Munich. There are a few other scattered companies doing it, but the only big name right now that I know of is Facebook. Other questions? Okay. Either I've done my job very well or very poorly, it seems. But hope you all had a good time.
Do you have cute puppies on the thank you slide?
No.
Go to my talk with cute puppies on the thank you slide.
It's just.
It's